Ladies and gentlemen, we now move to the most special program for today's agenda, for something which we have been waiting. Professor P.S. Rao's talk, titled A Few Milestones in My Research and Consultancy Career.
Professor Bhaskaramurthy, distinguished academicians and structural engineers of the country, I am seeing them in large number before me. Dear delegates of the Structural Engineering Convention, ladies and gentlemen, it's quite an honor for me that you are arranging a felicitation function for me on the occasion of my having completed 80 years on the 7th of November 1936. 1990, sorry, was born on 7th of November 1936, completed 80 years in 2016. I am grateful to all the organizers for this gesture. So I'll come back to proposing a formal vote of thanks from my side at the end of the function. But at the beginning, I would like to tell you about a few instances in my career which I was able to contribute, through which I was able to contribute to the development of the science of reinforced concrete design. It's late in the evening, so I am aware that all of you would like to go home, so I will not take too much of your time, but kindly give me some time to present a few facts before you. Before I go to the regular presentation, I would like to express my appreciation of the few people, the most important people who have been role models for me in my life so far. First, my parents. My father, a retired headmaster of a high school and principal of a junior college, a very strict disciplinarian and very well respected in the town. My mother, a devoted wife and a mother. I studied at IIT Kharagpur, both BTech and MTech, and my teacher of reinforced concrete structures at the BTech level was Dr. Malik. Unfortunately, he is no more. I don't have his photo also, that's why I'm not showing that. Professor Dr. Varghese, quite a number of you must be knowing him. All the people at IIT Madras know him as the first head of the Department of Civil Engineering, but I knew him much earlier. He was my teacher in MTech at IIT Kharagpur. So he was in a way a mentor for me in my initial postgraduate studies. Then the great master under whom I worked, Professor Rouge, Professor of Concrete Structures at the Technical University, Munich, who taught all his students, including myself, the purpose and methodology for research in concrete structures. Now I would like to go to, after having expressed my respect to the role models I had in my life, I would like to shift to my main lecture. And Professor Cordina, the leader of the German delegation, which helped us in setting up the structural engineering laboratory, once mentioned that a speech will be considered to be very great if it satisfies the following criteria. One third of the speech should be understood by everybody. One third of the speech should be understood only by 50% of the audience. And one third of the speech, nobody should understand. I have formulated my lecture according to that dictate, and I request you kindly to bear with me if you fall in any of these categories. The slide I am showing here is from IS 456-2000, the Bible of concrete designers in our country. This is the 2000 version of the Code of Practice. We had this code even in 1978. So, 40 years back almost. And must be familiar to all the civil engineers in India who have graduated after 1980. And the same code is in the Eurocode EN 1992-2004 version, but it was there 25 years earlier to that in the model code of CEP, FIP, the French word for Comité Européen de Béton, the European Concrete Committee. So in existence in the European countries for the last 40 years. In fact, we have borrowed it from the European code into our Indian code. And this is the same curve in Indian Roads Congress Code 112 as recent as 2011, borrowed from the European code. And this is the Japanese code. You see here the parabola and the rectangle. It's known all over the world as parabola, rectangle, concrete, stress block. Adopted in so many countries all over the world. This is the Hong Kong Code of Practice. Again, the same parabola, rectangle. Now, our teachers of reinforced concrete design in our engineering colleges all over the country must have been teaching this concrete about the concrete stress block, use of that for proportioning members, concrete columns, concrete beams, concrete slabs. Most of these members subjected to uniaxial bending, and must have used that particular curve simply because it was in the code. And not many people must be knowing from where it has originated, when it has originated. It comes from this publication dated August 1961. And where I had the good fortune to be one of the authors along with my and a senior colleague of mine, Professor Grasser. I went to Germany in 1959 as a DAD scholar. I reported to Professor Rush and said I would like to work for a doctorate. He said, I don't give doctorates just like that. Simply solving a few equations doesn't make you a doctor. I want the person who gets a doctorate from me, I want certain maturity from him. So I would like him to have an all-round development instead of merely concentrating on a small area. So first work on a research project which is ongoing, show your metal, then I will decide whether I should take you as a doctoral candidate or not. And I joined the team already working on a particular research topic, and that was on the effect of sustained load on the strength of concrete. It was a research project lasting for about 3-4 years. where specimens of this nature were tested. We have a load here, with some eccentricity here, and that eccentricity varies from 0 to 1/6 of the depth of the cross section here. And about 500 specimens were tested, subjected to different types of loading, different grades of concrete, different qualities of cement, different ages at the start of loading. And then what happens if I keep the load constant on the specimen for a few hours, a day, 2 days, 3 days, like that. Then we got this curve. I am explaining now how we got that parabola rectangle. It didn't come out of our head just like that. There was hard work and full justification for proposing that parabola rectangle in that publication which I showed you. And here you see the finding of that research project. It's all going forward only. I want to go backward. Yes. This is the short-term strength for 2 minutes is 100%. We usually test a cylinder, put it in a machine, crush it for just in a period of 2 minutes. But then you keep it for about 20 minutes, the load constant, the strength falls down already by about 4%. Keep it longer, 100 minutes, the strength falls down further. And up to about 4 days or something like that, of that region, 3 to 4 days, sustained loading, the strength of concrete falls by as much as 20%. Now for designing of concrete structures, we need information not only about the strength of concrete, but also the strain behavior of the concrete. And this shows the results of evaluation of one particular typical example, where the actually loaded specimen had a failure of 0.2% strain here. And only one strain is the uniform distribution, so the strain over the entire cross section is the same. You have more strain on one side, less strain on the other side. So you should have one particular strain on one side, another particular strain on the other side, epsilon 1 and epsilon 2. And you keep on changing the eccentricities, you get different combinations of epsilon 1 and epsilon 2, the two strains on the two faces. And then you try to fit in a curve which will fit the description that it has to have that eccentricity and that strain configuration. So like that, for a number of eccentricities, specimens were tested and the corresponding stress strain curves were drawn. And this is for one particular loading duration, 100 minutes duration. I'm giving only one example of the evaluation sheet. Like that, we did for different durations of loading and obtained the stress strain curves for loading for 20 minutes, loading for 100 minutes, 1000 minutes, 7 days, and so on. And you see that here you have the highest value of the strength, and here you have the lowest value of the strength. And you might have noticed in that earlier curve that after 4 days there is a reversal of the relationship. That was because of the aging of concrete. So we have decided that roughly 4 to 7 days is the critical period for getting the minimum strength of concrete. Now when you have so many stress strain curves, which curve should I use? That was a problem. I'm telling you the story of how that stress strain concrete was developed. Stress strain concrete curve was developed. So which curve shall I use? So we decided that we evaluate the strengths of the concrete members using all the curves and compare the load carrying capacity predicted by each of those curves. Now you get different curves naturally when you make use of different stress strain curves. Yes. And you see here, this is the percentage of reinforcement and this is the corresponding capacity of the member. And at one stage, the 20-minute curve gave the lowest value. At another stage, the 100-minute curve gave the lowest value. At another stage, the 1000-minute curve gave the lowest value. So again, we had a problem. And we can't have so many curves for the design of the concrete structures. So we should have one unified curve. And this is for pure bending. And these are the curves again. These are the well-known PM interaction curves, the concrete structure is small. And here again we have the same dilemma, but different curves gave the minimum strength for different percentages of reinforcement. So we decided that we go by the absolute minimum of all the curves put together and try to obtain a stress block which would give or reflect that particular phenomenon. It will be giving the values closest to the minimum observed by using all the several curves. And that is this curve. And believe me, I tested at least 8 or 10 different stress blocks with different combinations of those strains. We have 2, 3.5, 0.2 or 0.35% if you express, maybe 0.15, 0.25, like that, or a straight line and a rectangle, at least 8 to 10 different combinations, and finally arrived at this rectangle stress block, parabola rectangle stress block, and also obtained the relationship between the two its strains. This is a well-known equation, again connecting these two strains, available in the Indian Code IS 456, available in so many other international codes. So you need information not only about the maximum stress the concrete can take, but also the relations for the strains which the concrete could undergo. And here we have the comparison between the results predicted by the curve proposed by us and the minimum. I showed you the envelope of the minimums predicted by different curves, and they were differing only by an order of about 2 to 3%. Sometimes maybe smaller, sometimes maybe larger. The difference was only 2 to 3%. We were satisfied that with the curve which we have proposed, we are recommending a curve which would give the minimum strength under any circumstances. And that's what you need for the safety of a structure. So we decided on that particular concrete stress block with those particular strains of those particular stress values, 0.8 times the cube strength. And it was published in this around 1962. No, sorry, in 1961, which I showed you already. But then, when the European Concrete Committee came to know of this result of ours and the result of our studies published in the bulletin, the European Concrete Committee, consisting of representatives from several countries of Europe, including UK, they decided they would like to publish. French used to be the official language in those days. Now, of course, English has taken over. So they wanted to translate it verbatim into French and publish it as a bulletin of the European Concrete Committee. And it got accepted by the European Concrete Committee. It was built into the model concrete code, Euro code in the 60s. It was incorporated into DIN 1045, the standard, German standard. And then we imported it via all these different countries in 1978 into our IS 456. It continues to be valid even today. And even the latest revision of, I told you, IRC 112 2011 carries the same version. So I wanted to tell you about this contribution of mine for calculating the ultimate load capacity for the limit state of collapse of uniaxially loaded concrete structural members. Could be column, could be beam, could be slab. These are the main structural members. Could be footing, foundation footing. So the main structural members used in a building. Then this is already, I spent about 2.5 years as a research scholar. Of course, I got, in addition to the general government scholarship, because my professor was satisfied with my work, he took me as a research associate, used to give me a little extra stipend because of that. And then he said, all right, I am satisfied with your work, you go ahead with your doctoral work. You have contributed well enough for the limit state of collapse region, but then you concentrate on the limit state of serviceability. You determine how to calculate the deformations of concrete structures. Until now it was only the strength of the concrete structure. Now we come to calculating the deflections, the crack widths and so on. And so I had an entirely different assignment to find out, when the concrete member is loaded and it does get cracked. In fact, that's the reason why we put in reinforcement. All of you know that. We're all civil engineers. But then the crack width should not exceed a certain value, given value. But to find out the width of the crack that is likely to be developed, we should know how much of strain is developed at the level of steel. And that strain of steel keeps on varying. At a crack, it's large. At the next crack, it's again large. But in between the cracks, it is less because concrete also carries some strain. So we should arrive at the mean value of the steel strain. Unfortunately, formulae were available. And methods were available for obtaining the behavior of the concrete member in uncracked state, behavior of the concrete member in the cracked state, and what in reality is something in between. The average of the uncracked section behavior and the cracked section behavior. But no methods were available at that time. So I was given the responsibility of developing a method for getting that true value, and went on evaluating again large number of results already available in the laboratory, and proposed a method for calculating these mean strains. This is theoretical values, this is the measured values, and you see how well they are coinciding. And this again was incorporated into the report for the calculation of their formula, for the use of their formula for calculating the crack widths and deflections. This was published as a publication of the German Concrete Institute. Taken it again, DIN 1045 into the Euro code, into the Euro norm, which became official for most of the European countries later. Skip this detail. Yes, having contributed for determining the strength of concrete and also the deformations of concrete suitable for a design office, I wanted to gain experience also by interacting with industry. Prof. Rao was a very well-known figure, so we used to get a lot of structures, proof checking, and I was involved in some of these assignments. And this is a Lufthansa hangar at Munich Airport. Having a column-free area of 100 meters by 60 meters. In fact, prior to that, we had Prof checked a much larger area, 150 meters long, 60 meters wide, column-free, for accommodating 2 Boeing jets. For the repairs, of course, the maintenance hangars. That was built for a different company altogether. Lufthansa liked it so much, they wanted it to be built at Munich. And I gained rich experience of industry interaction and also solving practical problems by involving myself in such activities. When I came back and joined IIT Madras in 1965, the job given to me, one of the earliest jobs given to me, was using my German connections to plan the laboratory and order the equipment and commission the laboratory. And this is one view of the laboratory. This is another view of the laboratory. I don't want to go into further details. It was commissioned in 1971, and it was perhaps at that time one of the best laboratories in the country of its nature, and even today I can say with pride that it's one of the best laboratories in the academic institutions of our country. At that time, the laboratory was inaugurated in 71, 72. Ours was the only laboratory in the country having facility for dynamic testing, dynamic load testing. And that was the time when precious concrete sleepers were being developed. You know, when the train moves on the sleepers, it is subjected to dynamic loading. So RDSO also did not have facilities. So they approached us and we gladly accepted that, subjected the sleepers to all sorts of tests. These are from the specifications of Indian Railways. And these are precious concrete railway sleepers. We interacted with RDSO in improving and perfecting the design, and as many as about 15 sleeper factories in India today, or even perhaps even more, are manufacturing these sleepers in millions all over the country. In fact, one of the experts is here, Mr. Sreenivasa Rao is here, and he himself, their company, they themselves have offered consultancy to a large number of organizations how to produce these sleepers. We have looked into not only the technical aspects but also the economic aspects of how to finance that, how is the return in the first year, how is the return in the second year, all financial flow statements. We got involved in preparing detailed project report to be submitted to the banks for financing and so on. So that was the era of sleeper consultancy, I would say, 1970 to 1980. And a number of assignments we had from RDSO, Railway Design Standards Organization. I should acknowledge here that I had the benefit of excellent cooperation from my colleagues, Professor Ganeshan, Professor Rajgopal, who is fortunately with us, Professor Aravindan, and a number of others who helped me in conducting these investigations. When I was in Germany, I had a look at this Stuttgart TV tower built in 1955. The first TV tower in concrete, a beautiful structure designed by a very famous Professor Leonhardt. And when I first went to Germany in 1959, spent about 5 years before I returned. I had a look at this tower, and I dreamt at that time that we should have such towers in India also. But immediately after coming back, I didn't have a chance. But after setting up the laboratory and completing these investigations on sleepers and other assignments, towards the end of 70s or early 80s, I took up the task of designing top structures. I had to study the subject myself before I could teach others how to design. And I met the then engineering chief of Doordarshan, or India Radio, Mr. Darji. I told him some of the slides and told him that we should build such towers in our country. He readily accepted and said, all right, please give us the consultancy for that. We are prepared. Until that time, they were building only the steel towers, lattice towers. They are good, functionally very good, but I'm sure you'll agree with me that aesthetically, this tower looks much, much better than tower made of steel. So the CJAG have also agreed. I conducted a special course for them, their engineers. They got convinced that I had the wherewithal to be their consultant. They took me as a consultant for design of the TV towers in concrete. And during the period from 1970 to 1980, we have built about 30 TV towers all over India. You see those dots all in the entire country, for which I was a consultant for Doordarshan in the design of all the towers. The towers heights range from 100 meters, 120 meters to 330 meters. The tallest freestanding structures in the country. Most probably even today, they are the tallest freestanding structures in the country. Some of them. This is one of them, Rameshwaram TV tower, about 320 meters tall. Jaisalmer TV tower, also of that order, 320, 330 meters, of course including the steel mast which you have on the top. Concrete portion about 300 meters, and then antenna have to be, even if it is a concrete tower or a steel tower, the antenna have to be fixed onto the steel lattice right on the top. And then this bush tower, again the landmark of the order of 350 meters. Not that order, I am not remembering the exact heights. And this bush tower has a history. It was completed in around 1990, around that time. It withstood the very severe earthquake that rocked that area. Richter scale 8 closer earthquake. And this is a news item from February 2001, where it was mentioned towers to without any blemish. And I was lucky that my forecast came true. In 1990 itself I certified. We had carried out, somebody made a query, is the tower safe against the earthquake? And I gave the certificate that there is no harm, even if a very severe earthquake is reached. And I'm fortunate that my prediction, nothing happened to me. But then there is a technical reason why the particular tower did not have any damage. The taller the tower, the more flexible it becomes. And the time period of oscillation increases. The smaller the tower, it becomes very stiff, and the time period of oscillation increases. Now the frequencies, dominant frequencies, even earthquake, do not match with the frequencies of the towers if they are very tall. In fact, I heard C.V.R. Murthy mentioning yesterday that the maximum damage is observed only in buildings of the order of 3 stories and 5 stories. They are the predominant habitat structures in our country. But if you build a very tall building or a very tall tower, it's very flexible. The frequency of oscillation of the tall tower does not match with the frequency, the dominant frequencies of the earthquake. So wind, on the other hand, gains the upper hand, and they are much more vulnerable against wind. And we design, which is one area where we get the maximum earthquake forces and the maximum wind forces simultaneously. Nowhere else it happens. Maybe I think in the northeast region also it happens. You have very strong winds and very strong earthquakes. For example, along the east coast, you have only winds and no earthquake. So wherever wind is also very high, it governs the design of tall towers, not the 3-story buildings, 5-story buildings. In fact, this is an interesting statement showing the height of the tower and the corresponding period of oscillation. And we see the larger the higher the taller the tower, higher is the period of oscillation. That is more flexible. So my advice to all civil engineers, senior Murthy and his friends, that if you want to avoid damage due to earthquake, go for buildings larger than 20 stories. They will be safe. And the buildings which are only 3 stories high or 5 stories high, they are vulnerable. In the process of designing of the tall towers, I developed a passion for studies on cooling towers. Dr. Raman was mentioning about this during his first welcome speech. These are slightly different. The heights are not very high. It's around about 120 meters of the order. And the distinguishing feature is that the base diameter is comparable to the height. Huge, massive structures, 120 meters high, about 80 meters in base diameter. And the thickness, the wall thickness, is around the order of 150 millimeters in the upper reaches. And people have described that the ratio of the thickness of the shell, 150 millimeters, to the base diameter, is much smaller than the ratio which you find in an egg shell. Ordinary egg, it has a shell shape, oval shape, and it has a thickness, it has a diameter. You compare that ratio of that thickness to the diameter, and compare the ratio of this thickness, wall thickness, to the diameter. This is smaller. So it's a very, very thin member. So there is that's why there is a danger of possibility of buckling. We had concentrated investigations on buckling of concrete shells, these cooling tower shells. We proposed some increase in the wind pressure in the top regions of the shell, but somehow that didn't get accepted so far. I hope it will one day get accepted in the board. But on the other hand, all our studies on tall tower structures, when we were designing these tall tower structures, we were not confining ourselves only to checking the designs of somebody. In fact, we had to specify how the tower had to be designed, because during that time, the code was not, the Indian code, which now specifies the best factor approach, was not there. It came into existence only in 1987. In fact, most of our 87 version were published maybe in 1990. And most of the towers we built were completed by that time. We didn't have any code for designing. And we had to compare several national codes. And one code says something, another code says something else. Somebody talks of mean movement speed, somebody talks of 3-second gust, somebody talks of fastest mile of wind. The Americans do that, I never understood what it meant. So all different definitions of wind velocities, all different load factors. But that was a topic I gave to Dr. Felicitation, is study all these codes and tell me, or make your own proposal if you want to. That some sense comes out of this big bias that is existing. So at that time, we had to specify which particular code had to be followed by the designers. And we found that at that time, the Canadian code was the best available, and we reproduced that. I told the Russian people, please reproduce that Canadian code and make it a condition of your contract. Otherwise, designer A comes with British code, designer B comes with American code, designer C comes with some other code, then you just can't compare. So I told them, please go and specify the code, Canadian code at that time, the code which dealt with this gust factor method most elaborately at that time. And then we made our own studies, and I'm glad to inform you that some of the recommendations we made out of our own studies got incorporated in the latest IS 1998. That's been a corroborated statement. He is the chairman of that committee. And While designing these massive structures, we found that the design of the foundations also required special treatment. We assume the foundation slab to be rigid and calculate the soil pressures. But in reality, because the huge diameter ramps, the order of 50 meters, 60 meters diameter, and projections, cantilever projections beyond the wall. This projection, order of 15 meters, 10 meters, 15 meters, they are acting as cantilevers. So when the soil pressure is acting from below, they undergo deformation, and when the deformation, and then the soil undergoes deformation, the pressure distribution changes. And so one has to take into account the soil structure interaction. And we have revised our designers at that time to take that also into account and obtain corresponding economies in the design. You see the difference in the magnitude of the stress resultants. This assuming soil structure interaction, and the other one assuming it as rigid. So the country gained a lot of economic advantage by this recommendation. We applied the same principle for soil structure interaction for designing of harbor structures. The pile resting in soil, the soil resists the pressure, lateral pressure. When you have mooring forces pulling the berth here, the ships get berthed here, but then when the pile is pressing against the soil, there is a reaction from the pole offered by the soil, and if you use the soil structure interaction principles, again you will get very economical principles. So some of our research work was concentrated on that, and it was of great use to many port authorities in India. This is the work I was doing when I was at IIT Madras. I shifted to Visakhapatnam, became the principal of the Gayatri Engineering College in 1997. I was the principal for 10 years, and even today I am continuing my association with the college as an advisor. But I have always liked to interact with the industry. I gained by that, the industry also gained by that. When I became a better teacher, when I learned from the industry what is needed by them, what are their practices in the industry, I could incorporate that in my lectures to the students. And that's how we were integrated to that industry institute interaction at IIT Madras. I wanted to convey the same habit, same line of thinking to my colleagues at Visakhapatnam. In fact, some of my colleagues here who actually involve themselves in some of the consultancy activities. Professor Rao is here, the Dean of Consultancy with us. Professor Paparao is here, the head of the department. And they were responsible for designing a beautiful stadium in Visakhapatnam, the cricket stadium. Very beautiful, set amidst mountains, lovely stadium. And I remember one conversation I had with Dr. Sreenivasa. I am seeing here as Rao and Sons. And I told him that the first match conducted in this stadium was between India and Pakistan, when Pakistan was touring India. I think that was the debut match for Dhoni. Dhoni scored a century. That was the only match which India won in the series out of the 5. All other 4 games were lost. And I told Dr. Sreenivasa, where is he? I saw him. He said, the vastu of the stadium must be very good. And even today, it proves to be a good stadium for the Indian team. This was another interesting job my colleagues at Visakhapatnam, again, Professor Rao, Professor Paparao and others did. It was a German company, for a German company, who wanted to lay precast pipes 4 meters in diameter, length, I don't remember. What? Not 4 meters, I think 9 meters, 2 meters, right?
1 meter diameter, sir.
How much are that?
Diameter 2 meters, length 4 meters.
Right, you're right. Thank you. Thank you. And the interesting point was that they wanted to have a concrete strength of 20 grams per square millimeter at 16 hours without stream curing and with a slump of 150 millimeters using only ordinary mixer, no pan mixer. So all sorts of restrictions and wanted the strength of 20 grams per square millimeter. That is the strength which you get in 28 days normally. And the cement content not to exceed 400 kilograms per cubic meter. With so many constraints, they wanted my team at Visakhapatnam to develop that high strength. I'm glad to inform you that they succeeded in that and helped that German company. And it was used in building a tunnel-like thing. There was a river Godavari going across about 2.5 kilometers. They started boring from here, inserting the pipes from one end, inserting the pipes from one end, meet here at the center, and come out at the center shaft. It was a very, very interesting experience. Now, we are believing in interdisciplinary research. I'm trying to carry out some interdisciplinary research for the consultancy activity at the Gayatri University College of Engineering. I'm glad to show you here one instrument developed by one of our very talented colleagues, Dr. Tatavarti, using laser technology for measuring the wind velocity. Just one small instrument shooting out a laser from the center along the height, and it can go up to 200 meters, 300 meters. Take the refracted version from different heights, 40 meters, 50 meters, or 100 meters, 200 meters, and measuring the characteristics of the scattered light that comes back from these different heights that can be programmed. You can predict the wind velocity, the wind pressure, the wind direction, the wind density, all parameters which are required for the design of structures or for the design of wind power equipment. In fact, I met at Gomtanayan here. He's here. We are interacting with the National Institute for Wind Engineering in developing this instrument. I hope you are satisfied with what we have done at Gomtanayan. Thank you. Thank you. He's delivering a lecture tomorrow morning. So, these are some of the activities which we are continuing even at Gayatri Engineering College. I come back now a full circle, go back to 1960. The one which I showed just 1 minute earlier is about done for 2 months back. Now I am going back to 1960. This is the shell model I tested as an MTech student at IIT Kharagpur under the guidance of Professor Verghese. And Professor Verghese reported about this test in a symposium held on shell structures at the then CVRI, of which the structural engineering division was a part of that CVRI. The first director of SCRC here, Professor C.S. Ramaswamy, was the deputy director at Roorkee, CVRI Roorkee. So Professor Verghese reported about the results of my test on the shell model when I was an MTech student at that symposium held in 1960. And I am very happy that I am today presenting my presentation in the same SCRC but now at Madras on an entirely different scenario. And it's a coincidence that my first research work was presented at the Structural Engineering Division of CBRA at that time. Now my presentation today is at the Structural Engineering Research Center at Chennai. I feel happy about it. And ladies and gentlemen, I showed you, I started with a slide. where I showed photographs of my parents and my mentors as BTech level, MTech level, and doctorate level. And for a person to succeed, you require not only role models, but you require also people who support you in that activity. I have great pleasure in showing the team that supported me in all my endeavors in the last 50 years. My dear wife, Vijaya, and my 3 sons. One of them is here, Vamsi is here, the youngest of them is here, out of the 3. I am grateful to my wife for the excellent support she gave in taking care of not only me, but also of my 3 sons. Well, I had little time to spend with them, with my activities in the institute. And I'm grateful to my children also, because they took care of themselves on their own, without any support from me, but they may say without any interference from me. So I'm happy to acknowledge the gratitude, the debt I owe to my family members. Thank you very much, ladies and gentlemen.
Thank you, Professor. We now have the citation which will be read by Professor Devdas Menon.
Professor Rao, Mrs. Rao, Professor Bhaskar Ramamurthy, Director IIT Madras, Professor Santosh Kapuria, Director SCRC, respected teachers, so many of them, respected colleagues, dear students, citation for Professor Pullukurta Sreenivasa Rao. He obtained his BTech Honours and MTech degrees from the Indian Institute of Technology, Kharagpur in 1957 and 1958 respectively. He was ranked first in the Engineering Services Examination conducted by the UPSC in 1957 and second in the first batch of the Technical Teacher Trainees in 1958. Way back, I was born in 1958. Professor Rao obtained his doctoring degree in 1965 with the grade Ausscheiden. I hope Professor Rao speaks good German, but his disciples may not. But although it's Greek and German to us, what it means is it's the highest grade awarded by any German university, and he received this from the Technical University in Munich while working with Professor H. Riush. He joined the faculty of the Civil Engineering Department of Indian Institute of Technology, Madras in 1965 and was instrumental in commissioning the Structural Engineering Laboratory. During his career at IIT Madras, Professor Rao held many senior positions as the head of the Structural Engineering Laboratory, head of the Department of Civil Engineering, Dean of Industrial Consultancy and Sponsored Research, Dean of Academic Courses and Member Board of Governors of IIT Madras. He was awarded the prestigious Alexander von Humboldt Fellowship twice. Professor Rao has contributed immensely through his research in the field of reinforced and pre-stressed concrete, and many of his contributions have been incorporated in codes of practice such as DIN 1045, Eurocode EN 1992, IS 456, IS 4998, and IRC 112. He has also provided his technical expertise as a structural consultant on several challenging engineering projects worldwide. What you saw was only a small sample of what was actually done by him and all colleagues at the Structural Engineering Laboratory in IIT Madras. His research and consultancy works included applications to the design of pre-stressed concrete railway sleepers, RC towers, chimneys, natural draft cooling towers, raft slabs, pile rafts, shells and folded plates, stadia and port and harbour structures. With his penchant for deep fundamental understanding, he has guided 19 candidates for their PhD work and published more than 100 technical papers. In 2005, he was elected as a Fellow of the National Academy of Engineering, and in 2015 as a Fellow of the Andhra Pradesh Academy of Sciences. He was awarded the Indian Concrete Institute L&T Lifetime Achievement Award in 2008. He continues to be an advisor to the Gayatri Vidya Parishad group of educational institutions, which he helped found in 1997, and also as a structural engineering consultant for a number of organizations. The contributions of Professor Rao are truly immeasurable. We feel fortunate to have him amongst us today here, and it is with respect and affection we felicitate him this evening. We thank Professor Rao for his service and wish him and his family a long, healthy and cheerful future. We present this citation on behalf of all of you, and I request Professor Bhaskar Ramamurthy to kindly come forward to hand over.